Welcome to our first lesson in Chapter 9 of our organic chemistry journey. This chapter is focused on the functional group of alkynes, the triple bond. I've kind of color-coded for us our topics involved. Lesson 1, in this particular video, we're going to focus on the introduction to alkynes, remind us about their sp hybridization and their 180-degree bond angle. In this section, we'll explore that sp hybridization in terms of 1 sigma and 2 pi bonds with that 180 degrees, a very linear relationship there between the carbons. We'll practice nomenclature of the alkynes, acidity of the acetylene and terminal alkynes. Just interpreting that, it says this hydrogen on the end of an alkyne is very acidic, and we'll do some acid-base chemistry. And in our fourth lesson, the preparation of alkynes. How can we make an alkyne from something called a di-substituted alkyl halide? Very similar to the lessons of alkene. Those 4 sections will be the focus of this first lesson in Chapter 9. So let's get started. We remember from our very first introduction in our chapters relating to alkane, all single bonds, an alkene that has a double bond, and the triple bond, the ene. Alkenes are compounds that contain a triple bond. With this Y, we want to emphasize how to say that between ene and eine. Ane is a single. Ene has a double. And of course, the eine ending, if you hear that on an alkyl chain, you know it contains a triple bond. And recall that a triple bond contains 1 sigma, and that sigma bond lies within the axes. So here in the same plane of the nuclei is the sigma bond. And the pi bonds rely on top and bottom, creating that triple bond. So it's sp hybridized. The s and the p orbitals are creating a triple bond. And it is a linear configuration in that 180 degrees. So straight out from each carbon in either direction. Notice that this is a very electron-rich area. Very similar to the alkenes, these pi bonds have the ability to reach out and abstract a proton. Very similar to the alkene chemistry from our previous chapter. So they're very reactive, similar to alkenes as nucleophiles if they're seeking an electrophile, or they can be bases seeking a proton. Let's practice the nomenclature of alkynes. Now, alkynes are named with very similar rules and procedures as discussed in the previous chapter 4, naming alkanes. Then we practiced alkenes with the EZ, cis or trans. Here we'll have none of that and just simply find the longest carbon chain that includes the C triple bond C. So step number 1, when we begin naming our molecules, let's find the longest parent chain, and that parent chain must include the triple bond. We'll identify and name all of the substituents. We'll assign a number, a locant, a number to each substituent, giving the triple bond precedent. The triple bond must have the lowest number possible. So it is given the priority when numbering. Then, of course, we know to number the substituents before the parent name in alphabetical order. We ignore prefixes such as secondary butyl alcohol. We would ignore anything other than iso. Like if we had a tert butyl, we'd ignore the tert and go with butyl. And I remember learning that iso, let's take an example, isobutyl. The isobutyl, notice there's no hyphen in this name, so the I is what we would alphabetize with. If we're naming a sec-butyl, we see that there's a hyphen there as the B gets precedent. And of course, tert butyl We would also go with the B when alphabetizing because the hyphen is letting us know just what part of the carbon it's attached to. So a tert butyl, if you remember, would have 4 carbons, and then here is the site of attachment. So this, again, is tert butyl. Sec butyl, just to remind ourselves, would have 4 carbons, but the carbon is attached to the parent chain at carbon number 2. So that would be sec butyl. And with tert butyl, isobutyl, you have this carbon kind of branching out at the end, and the R group would be numbered with 1, 2, and then a branch at the end. That's the isofunctional group. And we do indeed alphabetize by I for iso, but we go with the butyl for sec or tert. Just a reminder from a previous lesson. I'm sorry if I digressed. Remember that as we're naming the parent chain, the "-ine" ending becomes part of the suffix. So let's give this a little bit of detailed attention. Kind of practice those 5 rules. Just to remind ourselves about the ending. When we see an all saturated hydrocarbon chain, all single bonds, we hear the "-ane" ending. 1, 2, 3, 4, 5. The parent chain is pent, ending in "-ane" to indicate all single bonds. When we named -ines, the double bond, we find the lowest number possible when we name these. 1, 2, 3, 4, 5. Between carbons 1 and 2, we have a double bond. So we name that between carbon 1 and 2. We would name that 1-pentene. And now notice what here. Let's just emphasize something. Carbon 1 has 2 hydrogens coming off of it, and carbon number 2 would still have 1 hydrogen coming off of it, but I want to emphasize this is 120 degrees. This is called trigonal planar. Boy, this pen is not writing well. Let me try that word again. Sometimes I have luck if I just change to a thinner line. Trigonal planar. Nope, that's not coming out well. I'll just say it. Trigonal planar, 120 degrees for that bond. And with the -ine, we see it's a triple bond with 180 degrees. When you're naming, make sure that the triple bond has the lowest possible numbers assigned to it. Here we have, for example, a carbon chain that is 7 carbons in the longest parent chain. We would begin numbering from left to right, making sure that we would call this kind of one step at a time as a heptine. Hept is the prefix for 7. Ine is the the suffix for a triple bond. And notice that it begins at carbon number 2, so we hyphenate that. And what is incorrect is to begin numbering in a place on the right side, going from right to left, and the carbon triple bond would end up between carbon 5 and 6. So just a note, remember to find the carbon triple bond and give it the lowest number possible. Now to just kind of figure that out, notice that we have some substituent groups here. We have a methyl group at carbon 5, another at carbon 5, and another at carbon 6. So listing those, we would have 5, 5, 6, and that is trimethyl, all one word. And then hyphen 2-heptine. So we labeled all 3 methyl groups by position. Another note to make sure that even if you have a longer carbon chain without the presence of the triple bond, for example, here I could number 8 carbons as an octane, but that's not correct because the parent chain must contain the triple bond. So I do not number it in that order. I number it as carbon 1, 2, 3, 4, 5, 6, 7. And this would become a propyl group. This would look like 3 propyl. Tell me where that triple bond is. It's between carbon 1 and 2 in a 7 carbon chain of heptyne. We want to name and assign a number to the alkyl substituents, and alphabetize them. So with this particular example, we worked right up here, but we found that there were 3 methyl groups and we ordered them as 5,5,6, trimethyl, tell me where the double bond is, 2-heptyne. I wanted to make a note that it is absolutely okay to place the 2 in front of the parent, heptyne, or some people prefer to put this as all one word, trimethyl-hept, then the dash, 2-ine, letting you know where the triple bond is located. I tend to use this method. I think most people do, but this is also a correct IUPAC name. When we look at some common names, we make a notice here that acetylene and ethylene are the same name. Hear this prefix ethyl? That's telling us that we have 2 carbons involved in the triple bond. So notice that each one of these has acetylene as its root word. It's a common name, not IUPAC, but a lot of people still say acetylene. So acetylene is a 2-carbon, triple bonded functional group in a common name. Not IUPAC, but it's common. So here, notice that if I have a methyl group, right here is a carbon with 3 hydrogens, we would call it methyl acetylene. Here is our acetylene, and hanging off of each side is an isopropyl. So that's di-isopropyl acetylene. Here is a functional group phenyl. Here is a functional group propyl. Notice that they alphabetize. And in here that as phenyl propyl acetylene. Let's just really focus and say those are common names not heard of in IUPAC. You will be asked in this chapter to write a standardized name from the IUPAC system, a systematic name from the International Union of Pure and Applied Chemistry. Another definition you'll hear in this chapter is called a terminal alkyne. Notice the position of a terminal alkyne is at the end of a carbon chain. Between carbon 1 and carbon 2, there will be a triple bond. And that's very important because this particular hydrogen at the end of that triple bond lays 1 more hydrogen. This is a very acidic hydrogen, and that will be part of the chemistry coming up soon with acids and bases. If you see the triple bond in the carbon chain, we call it an internal alkyne, and you might see that actually rearranged to create the more stable configuration at the terminal end. When we practice, we're doing some of your homework from Skillbuilder 9.1. Let's take a peek at the first example. Your first homework question is from Skillbuilder 1. We'll use it as a practice. It says, let's provide a systematic name. So one of our first steps is to find the longest carbon chain that contains the alkyne, and I see that it's at a terminal position. So right off the bat, I can recognize that that's carbon 1, 2, 3. Now I have to go in either direction and find the longest chain, and I clearly see that going to the right provides the longest chain. Then we'll kind of figure out what are our substituent groups. This looks like a propyl, a 3-carbon chain at carbon number 3. At carbon number 4, there's 2 carbons. That's called an ethyl. And at carbon number 5, there is a 1-carbon branch, and that's called a methyl. We have to alphabetize them when we name them, not priority by number, but by the alphabet. So at carbon number 4, I see that there is an ethyl group. The next letter would be the methyl. At carbon number 5, there is a methyl group. At carbon number 3, there is a propyl group. And now we're ready to name that parent chain. The root word, of course, is hept for number 7. But I also have to let you know, and I'm going to ran out of room here, so I'm going to come down. I'm going to have to let you know that at carbon number 1 is the triple bond, and the root word is hept. The suffix is -ine. 4 ethyl, 5 methyl, 3 propyl, 1 heptyne. Let's process together what we did. Step 1 and 2, we found the longest parent chain, and we numbered it, knowing that the number had to come from the triple bond being carbon number 1. That gave us the root word heptyne. We identified the substituents and named them. We found a propyl, an ethyl, and a methyl. From there, just to get back on the strategy, what we did then was to assemble the name and list them alphabetically. And when we listed them alphabetically, we found our name: 4 ethyl, 5 methyl, 3 propyl, 1 heptyne. Alphabetical: E, then M, then P. Tell me the position of the triple bond in the 7-carbon chain. When I see a number 1, I know that the triple bond is between carbon 1 and carbon 2. Excellent work. Try some yourself by pausing the video, draw the structure, and just give yourself a chance to name it. Don't cheat yourself of the chance. The learning builds as you practice on your own, and when ready, start the video back and let's check them together. Welcome back. Let's name a systematic name for each of the following compounds. We have to find the longest parent chain, and this is not branched. So if I number from left to right, I come up with a 6-carbon chain. Suppose I had numbered from right to left. Because this is a symmetrical chain, either way, we find that the triple bond is between carbon 3 and 4. So in this way, it did not matter which direction we numbered. Between carbon 3 and 4, there is a 6-carbon chain. Hex is the parent name. The ending is -ine to represent the triple bond. How'd you do? Here in our next example, again, an unbranched chain, a very simplistic model, but I do want to emphasize that we number from right to left to be sure that we are giving the triple bond the lowest number possible. Between carbon 3 and 4, the parent chain is oct. There is a triple bond. We call that 3-octyne. Okay, those were pretty easy. I hope you did well. How about letter F of your skill builder? This one's more challenging, but is it? Let's see what we have. If you'd like to pause the video, please do and work it out first. Come back when ready. I have to give the carbon chain the lowest number for the triple bond, and I keep numbering to find the longest carbon chain that contains the triple bond and give it the lowest number possible. So far, between carbon 3 and 4, in a 10 carbon chain, there is a triple bond, 3-decyne. What else do we have? Well, I notice at carbon 7, there is a methyl and another methyl. There's 2 functional groups. We'll end up saying dimethyl. And at carbon number 5, there's a 2-carbon chain, so we see that as a branch known as an ethyl. So let's put this together. Alphabetical. At carbon number 5, there is an ethyl. At carbon number 7 and 7 again, there is a dimethyl. 3-decyne. We have all 3 branches named. We've located the triple bond, and we've listed them alphabetically. Beautiful. You'll have some more practice with your Skillbuilder. Let's turn our attention to the next topic, acidity of that terminal alkyne. The terminal alkyne is, just to remind ourselves, it's when the triple bond lies at the end and we're looking at that particular proton. Friends, if you can find your pKa chart from an earlier acid-base chapter, you would find it extremely helpful, as we have to predict if a reaction will occur based on the pKa values of the acids in the equation. So here's a little review of something earlier called the pKa values. The very substrate here known as the alkane. With an alkane, we know that all single bonds occur. The pKa value is a very large number, 50. And what that's ionizing, just to remind yourself, that's this H. How easy is that to remove in an acid-base reaction? A little bit stronger is the ene, the alkene, in terms of the acid. How easy is it to remove the proton from the alkene? Keep in mind the electron density is getting richer in this pi bond, making this region a little more negative and this region a little more positive as compared to the ane. The more positive means that the polarity is reaching out for that pi bond there, makes it easier to pluck off. And now look, the pKa of the ine, the terminal hydrogen here in a triple bond, is extremely acidic. This hydrogen here at the end of the triple bond is very easily removed simply because we have the triple bond is very, very electron rich, making this hydrogen very electron deficient. So notice that the very acidic end of the ethylene is about 10 to the 19 units times stronger in terms of the alkane. So it can be deprotonated in an acid-base reaction. Let's take a peek at what we remember as conjugate pairs. Here's a molecule we're learning as a common name called acetylene. It's the simplistic form of a C triple bond C. This is the proton that a base will reach out for. A base, let's just say, for example, an electron-rich nitrogen. That's an example of a substance that will act as a base. And we don't call it a nucleophile here because we're abstracting a proton and not like a positive carbon and a carbocation. So acid-base chemistry. Acetylene is acting as the acid because it's going to have a proton donor. This is going to release its hydrogen. And the base is going to accept that proton, and we actually form conjugate pairs. So notice if I pluck off the hydrogen at the end, the bond collapses and we get an acetylide ion. Let me emphasize, it's a carboanion, a negative ion, carboanion. And of course, the other conjugate, if I just make up that example, would be ammonia. And just based on its distribution here, remember this would be a negative charge based on formal charge. The base reaches out, adds its proton on. So we form conjugate pairs where we have a base forming a conjugate acid and we have an acid forming its conjugate base. And just as a reminder, when we form these carbo, and we really get rid of the double vowel and we just say carbanion. It looks like a pie. Carbanion, a negative ion. There we go. It's most stable with the pi bonds here in the triple bond and less stable down here with a single bond sp3 hybridization. And that just has to do with the lone pair occupying the sp orbital being most stable with that pi bond right next door, electron-rich area. So as we explore that last hydrogen, the terminal hydrogen on an alkyne, a strong base will deprotonate, and what happens is that it forms conjugate pairs. So let's practice, and this is a review lesson from our acid-base chapter, but repetition's our friend while we're learning, no problem. Bases and conjugate acid pKa must be greater than 25 for it to be able to deprotonate a terminal alkyne. And let's understand this sentence. If you look on your pKa chart, the value for the pKa of a terminal hydrogen of a triple bond is 25. So that means that we have to have something weaker form, and this is the acid. We have to have something weaker form because I understand that the equilibrium favors the weaker side. And in this case, the ammonia has a pKa of 38. The acetylene, this terminal hydrogen, has a pKa from 25. And if we don't remember how to read that chart, I'll show you the chart in the next slide. But we want to make sure that we go from stronger to weaker in order for the reaction to favor the product side. So here we looked up acetylene 25, and that's a number you're just going to get used to looking up so many times that you'll remember the terminal end of a hydrogen there, the terminal end of an alkyne has a pKa of 25. For the reaction to proceed favorably forward to favor the right side, you need a pKa with a number greater than 25 to push the reaction forward. Let me model this. What about this equation? So here I have sodium hydroxide, NaOH, reacting with acetylene. The terminal hydrogen has a pKa of 25. We form conjugate pairs. The hydroxide group reaches out for the proton. This bond collapses. When that bond collapses, we form a carbanion, a negative ion with a negative charge. Here, the pKa of your acid was 25. I look up the pKa of water. Again, use your pKa chart. It's a number 15.7. That means that this is a stronger acid and that this is a weaker acid based on their pKa values. So clearly the equilibrium favors the weaker side. This reaction does not push to the forward direction. It lies to the left side with the acid itself, the acetylene, not being deprotonated. Here's a quick kind of a picture of, in the current chapter, of a pKa chart. So notice that this is the negative ion, carbanion. which results after the acetylene has been deprotonated. And so NH2, and just remember, Na is nothing but a spectator. It's the NH2 that really relies as being the base to deprotonate the terminal end of an alkyne. But it's not the only one. Here's the pKa's. And again, this is just a small picture of the larger pKa value of a chart I gave you earlier. If you still have that, pull it out of your notes. But in this chapter, they give us an abbreviated version. Here's that number, 25. I said you'll just get used to looking it up so often. You'll remember that a terminal alkyne, and all that means is that this is the hydrogen at the end of a triple bond chain. So I have a long carbon chain, and at the very end, I have a C triple bond C and a hydrogen. That's the hydrogen that's acidic. That's the proton that is going to be removed in an acid-base transfer. So what kind of things work well to deprotonate this acetylene? Well, anything above, such as a hydride, amide, and even an alkyde ion. So we have these types of values. We need a strong base, stronger than the terminal alkyne. And notice down here then, these oxygen compounds are not strong enough for actual chemistry to occur. So these are the bases that will not deprotonate the alkyne. Look on your pKa chart, it's hydride or above in this chart. So let's model that. It's actually kind of easy. It just comes back to us with practice. This example is coming from your homework. It says use your table 3.1. Well, that's the pKa chart. And again, I just took a quick snapshot and put it on this screen so that you would have enough to answer this question. You have access to your pKa chart. Here I have a cyclohexane and a terminal triple bond with a hydrogen. So this is the acidic hydrogen. And what it's going to ask us to do is kind of finish the chemistry. If we call this an acid, this must be the base. What comes out on the other side, and does it actually work? So let me redraw, and you draw it with me. A cyclohexane, and we have a C triple bond C and the terminal hydrogen. We're adding it to a base which contains a carboxylic salt. So we have a C triple bond O, O negative. And remember that the sodium is there really as a spectator. This electron-rich area on the oxygen is going to reach out and pluck off that proton from the acetylene terminal end, and the bond collapses onto the carbon. So when we redraw, we end up forming the carb anion. Here's the negative charge, and the acid that formed now has the OH, that's an O. This is known as a carboxylic acid, the OH. And remember now, the sodium will actually kind of float over to neutralize the charge on the carb anion. So will this reaction occur, is what it's really saying. Is this a good base? Is it strong enough to make this reaction occur? So notice again, just looking this up so many times, the pKa of a terminal end alkyne is about 25. This is the acid. On this side, this is the acid, the carboxylic acid. COOH, carboxylic acid. And it has a pKa of 5. Find the two acids. Here's the acid. Here's the acid. When you locate the two acids, look up their pKa values. This guy was 25, This guy was plain old 5. Is this reaction going to work? Well, based on our pKa values, you can see that the carboxylic acid is a stronger acid. This is a weaker acid. And so the equilibrium clearly lies to the left. So no, this base is not a good choice to deprotonate that particular acid. You try one. A homework question from Practice the Skill 9.5. And again, notice I put a little snapshot of the pKa chart from your chapter 9. You probably have another pKa from a photocopy I gave you before. Determine if this reaction will occur. So I want to finish the reaction. And remember, when I see NaNH2, sodium amide, recognize sodium is a spectator, but the base is the NH2 electron-rich nitrogen. All right, and it's carrying a -1 formal charge. So this hydrogen, the terminal end of the triple bond, this is the chemistry that will happen. We want to find the terminal hydrogen on the triple bond. That's the acidic, or the proton that is going to be plucked off. So we'll take our electron-rich nitrogen and we're going to take the hydrogen from the alkyne, and this bond collapses. So on the product side, we still have the triple bond, and it leads to our trimethyl area. Let's just make sure we're counting 1, 2, 3, 4. 1, 2, 3, 4, and then the 2 methyls coming off. This is an electron-rich area, so just notice that there's a pair of electrons and a negative charge. It is a carb anion. So that means that the sodium now will be floating next to it to equalize charges. And in addition, we have ammonia, NH3. The hydrogen added on, we label this the acid. Here is its conjugate base. Here is the base. Here is its conjugate acid. Find the 2 acids and look up their pKa values. And again, enough repetition, we remember 25 is the pKa value for a terminal hydrogen of an alkyne. Let's find ammonia, and it has a value of 38. This is a weaker acid. That didn't come out well. A weaker acid. So this equilibrium definitely lies to the right-hand side. And so yes, this is sufficiently strong to deprotonate the equation. It works. In our next section, let's talk about preparation of an alkyne. And luckily, there's a lot of overlap from the alkenes that we were just practicing in chapter 8 and 7. Just like the alkenes, how they were prepared from alkyl halides through an elimination reaction of a beta hydrogen, alkynes are prepared in exactly the same way, except we need 2 halogens on that carbon chain. So let's remember, here I have a carbon chain that has 2 bromines. So we would call this a dihalide. Notice that here is a bromine and here is a bromine. So it's a dihalide. In an E2 elimination bimolecular E2 mechanism, we're going to grab the beta hydrogen. So this would be alpha. The carbon that is attached to the halogens is known as the alpha. Here is the beta. The beta carbon has 2 hydrogens. The base is going to abstract off, pluck off the proton from the beta carbon, and this bond collapses. Notice at this point, the removal of 1 halogen creates an ene. The alkene has formed. In a second step, and you'll literally see on the arrow, a second equivalence of base. A second mole of base now goes after the second beta proton, and it abstracts, bond collapses, and the leaving group leaves. So in a sequence of 2 steps, each of the halogens is left as a leaving group, and we're left with an alkyne. There are 2 leaving groups. They're both halogens. There is a stepwise mechanism. 1 leaving group leaves, and in the next equivalent of base, the second leaving group leaves. And remember, the beta hydrogen then collapses and forms the pi bond. 2 equivalents of the base in this mechanism. And let's emphasize, it really doesn't matter if you have the bromine on the same carbon in that carbon chain. If it's on the same carbon, the definition is called a geminal dihalide. But notice that I still end up with a triple bond because the abstraction of the beta hydrogens occur in a stepwise fashion. It can also be a vicinal dihalide, and that definition just simply means that the bromines can be on neighboring carbons, on carbon 1 and on carbon 2, because here is the beta hydrogen for this bromine when it leaves. Here is the beta hydrogen for this bromine when it leaves. So that second elimination occurs like step by step, either in a geminal position or in a vicinal position. You end up with the exact same product. A 2-step elimination reaction. What if a third equivalent, or sometimes on the arrow, you'll see excess amounts. That's my abbreviation for excess amounts of base. Well, something unique happens there, and it really is easy to fix, but I just want to kind of emphasize, if you have excess amounts of the base, it goes through a 3rd step. So let's kind of take a moment and see. Here we have a dihalide, 2 bromines on the same carbon. Do you remember the vocab if they're on the same carbon? On the same carbon, did you look? It's called a geminal dihalide. Through 2 equivalents, we end up producing the ine. So that's 2 elimination reactions. Just to remember, 2 steps, 2 E2 mechanisms. Step number 1, just to remind ourselves, the base removes an HBr in the first step, forming an alkene. And in the next step, it removes the second HBr in the beta position compared to the bromine, and we'd form the triple bond. But now remember, we just learned that this proton at the end of a triple bond is very much an acidic proton. And this is very much a basic equivalence. So we're adding a base to a very acidic proton of an ine. So if I cannot control the amount and I have excess amounts, we'll go all the way to the carb anion formation. Notice that we have the negative ion forming, the alkynide ion. But it's easy to fix if you just do a next treatment with water. So often you'll see water sitting under the arrow to say, all right, well, let's just take that water and use it to put the proton back on the terminal alkyne chain. And what we've done then is form more conjugate pairs. We end up with an ine, and we formed conjugate pairs where we end up with this hydroxide ion. And the sodium, always the spectator, just floats to the negative ion to make sure it's electrically neutral. So in summary, this is how we make a terminal alkyne. Notice on the arrow, I see excess amounts of a strong base. That means in the first step, I'm going to extract, just to kind of think about what's happening here. In our first step, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One of the hydrogens and one of the bromines has been taken, and we have the double bond that's formed. So in the first step, the halogen leaves. The hydrogen, of course, gets plucked off, and this bond collapses. Now in your second step, we have that next strong base, the next equivalent, reaches out and abstracts that proton. The bond collapses and the leaving group leaves. So at the end of the second mole, or the second equivalent, we have a triple bond. And this has a very acidic proton. So the excess amounts of the base, and that's the critical thing here, the excess amount of the base says, I can take you, that last hydrogen, I can take you off the terminal chain, and what happens next is we end up with the negative carb anion, and of course the conjugate acid of the base. And then that's the job of the water. Let's add a water molecule that says this negative ion can then reach out to reprotonate itself by just taking that proton off of the water. And so finally, with that last treatment, we're going to end with a neutral alkyne. I still have 5 carbons in there. Although, thank you, I should number from the other direction. Carbon number 1, 2, 3, 4, 5. And then, of course, since I removed this, we'd have a hydroxide as a leftover negative ion. And of course, that's where the sodium will be as well. So kind of a stepwise mechanism to let you know this was the overall process. With excess amounts of base, I have to reprotonate with the water, and we end up with a terminal alkyne. Remember the title of this section? How do we make an alkyne? Well, we use a strong base. Let's practice one. Conceptual checkpoint 9.7. Predict the major product. I have excess amounts of base, and I end up with some water to make sure I reprotonate. Here's carbon 1, 2, 3, 4, just to make sure I end up with the same. 1, 2, 3, 4. Couple of methyl groups. The bromines have been abstracted. Well, let's do this. I'm going to redraw because my bond angle is wrong. I apologize if you just had to scratch that out. 1, 2, 3, 4. So, of course, thinking about our reaction, we have the amide, which carries that negative charge, reaching out for the beta protons. So right here on the first carbon are beta hydrogens. Notice on carbon 3, there are no beta hydrogens. So there are no competitions where to place the triple bond with this reaction. At carbon number 3, this carbon is bonded to all carbons, so there are no hydrogens there. So there is no competition. The only beta hydrogen is at carbon number 1. And so that's where the first abstraction will occur. I'm going to take off one of these beta hydrogens, and the bond collapses, forcing one of the leaving groups to leave. Step 1. In the first process, we have still our 3 carbons at the end. And now all of a sudden we ended with sp2 because we have a triple bond right here. There's 2 hydrogens left, and there's 1 bromine left. There was 3 hydrogens. We've removed 1 to give me sp2 hybridization and 120 degrees. That's why I wanted to erase and make sure that you see this bond angle is 120 degrees. In the next step, we have the next group of the base react, and this will be the next NH2 negative, the second equivalent. The second equivalent is going to reach out for another beta proton, making this bond collapse, and the leaving group leaves. So now here's my carbon that has kind of those 3 branches still. The carbon here, and now all of a sudden it goes to a triple bond, and now I've become very linear. It's sp hybridized, 180 degrees bond angle, but it still has the last hydrogen, right? Of the 2 here, there's still 1 left. But there were excess amounts of the base. So because I didn't control the equivalence, I put in all kinds of base, I still have a next abstraction. So just emphasizing the mechanism, the terminal end of an alkyne is an acidic proton. And so we still have a next reaction that occurs. I have that carbon that has 3 carbons coming off. Here's the carbon leading to the triple bond, but the hydrogen is gone, giving me the carb anion. Boy, that's not writing well. The carb anion is going to react with the water, and that's finally, just to kind of emphasize, remember the water was on the arrow? So the water now finally plays a role. And what happens is this negative ion reaches out and abstracts a proton from the water and just reprotonates the carbon terminal end so that it now is an alkyne. We also have the deprotonated water, which is now represented by hydroxide. And of course, we added the sodium to create an electrically neutral compound. Ultimately, it just simply asked, what was the major product? And I rambled. All you had to write about was the terminal alkyne that is produced. And notice it is sp hybridized. At the end is a terminal hydrogen based on reprotonating with the water. And make sure you notice it's 180 degrees when you draw that. That ends our lesson. And next time we pick up, we'll look at some more chemistry of alkynes. Great work today.